So our next speaker is Javier López. Javier is also a former student from our group. He now works in a very strange theme for me, which is binary obfuscation. It's not what he is going to tell us, or not exactly.
Not today.
But I mean, he is quite deep in compilers implementation details. And he is going to give a talk about exceptions, which I think we should be using more. So thank you very much, Javier, for being here, and the floor is yours.
Thank you for the presentation. I hope that the mic is working.
It looks like.
Okay, perfect. So yeah, as Daniel said, we're going to talk about exceptions today, but in a different way from what you're probably familiar to. First of all, who am I? Daniel also already introduced me. Yeah, I basically get the doctorate here. Then I started as a postdoc at CERN, mostly in the root group, where there is already some people here today that also come from the same group. While there, I was working for the R-tuple columnar storage system, but also for the Cling C++ jitter or / interpreter, which you had a talk on Clown REPL and Cling yesterday and Lib interop. And nowadays, I'm basically working as a senior compiler engineer in the area of software obfuscation, as Daniel said, and also became a WG21 member. Before starting the session, I would like to thank my friend Richard, who is the one that introduced me in this magnificent world of exception handling. Thank you. And before we start, I would like to take a bit the temperature of this room with a small C++ exception trivia. So question 1, myth or truth? Exception handling is slow. What do you think? Raise your hands, the ones that think that it's slow. Okay, yeah. So it's neutral for you, I guess. Depends. Okay. The ones that think that it's not slow. Okay. And neutral, the rest, I guess. Okay, yeah, maybe. Most of the time it's actually yes, it's quite slow. I mean, I wouldn't use it for my normal control flow, but most of the time it's okay for, dealing with errors and exceptional situations and whatnot. Most of the implementations are quite slow, by the way, but some others are or might be a bit better at that. Second question, can exceptions propagate through code that has been compiled with no exceptions? So just imagine the following. You have some call stack, you have some function at the bottom that appertains to some translation unit that has been compiled with exceptions enabled. Then you call some other functions that belong to other translation unit that was compiled with no exceptions, and then you have something at the top of your call stack that was compiled again with exceptions. If I throw here and try to catch at the bottom, will it work? Yes? Okay. Who thinks it shouldn't work? Okay. And the rest doesn't have any clue, I guess. Okay. The answer is yes, it will work. Actually, I would say most of the time, at least. No, it will work in most implementations. Actually, instead of that, if you call, well, I'm not going to do a spoiler because it's the next question. So yeah, the compiler will generate some additional opcode, some meta instructions, let's call it this way, some assembler directives to be able to unwind the stack for those frames that are in the middle as well. So you can throw here, cut here, but you need those stack frames that are in the middle need to be unwinded. And the assembler will, well, the compiler frontend actually will try to make that possible. We will see more about that. Don't get frightened if it gets confusing for now, but we will see throughout the presentation, we will see more details. Now, question 3. Do you think that C code can be compiled with thus fexceptions? Who thinks we can do it? Who thinks we cannot? Raise your hands. Okay, and the rest confused by this time, I guess. Okay, neutral. Okay. The answer is the same as in the previous question. So if you have, let's think this way. You have some C++ code that calls C function, which is whatever, and has been compiled with thus fexceptions. The actual thing that happens is that these fexceptions is most of the compilers just ignore it, and they still produce what is needed to be for these stack frames to be unwound. Again, more on that later. Question 4, and the last one. Exceptions are appropriate for embedded systems. What do you think? Would you use them in an embedded system? Yes? Okay. No? A few? Okay. And the others, neutral? No? Okay, I would say that it depends. For example, if your embedded system doesn't have any real-time requirement, I would say it's mostly okay to use it. If it has some real-time requirement, I wouldn't use it because it has non-deterministic unwound time. So yeah, that might be a problem in your use case. Yeah, depends on your tool chain, actually. Yeah, it depends on your tool chain. So yeah, believe it or not, this is the only C++ code that you will see in this presentation. Yeah, so you don't have to make sense out of it because it doesn't have any sense. It's just a piece of code that I managed to write that exercises everything that can happen with exceptions. So we have, where is the pointer? Here. So we have some function try catch block here that allocates some automatic storage that needs to be released by the time we land here at the catch block. We happen to call some function that has a try catch block again, some automatic storage here. There is a catch all here. This ends up calling some function. We do something, and then we conditionally throw if something happens. Okay, so far so good. This is the whole agenda for the presentation. We are going to go through some introductory slides that talk about ABIs and whatnot. Then we will talk about the Itanium ABI, which is, you will see that it's the most popular nowadays, except for MSBC. Where is Gavi? Okay, I don't know. Whatever. So we will next talk about what does the Itanium ABI says about the exception handling. Then we will shortly talk about the actual representation in the executable format. And then we'll, I mean, theory is good, but we will try to also accompany it with some practice. So we will try to watch it work and what actually happens when I throw an exception. And then we will wrap up this, hopefully in 55 minutes or so. So let's start with the introduction. So I would like to start with a brief definition from Wikipedia, saying that exception handling is the process of responding to the occurrence of exceptions, that is the anomalous or exceptional conditions requiring special processing during the execution of a program. In general, an exception breaks the normal control flow of execution and executes a pre-registered exception handler. In programming languages, because there is also hardware exceptions, right? This is most likely, well, you prepare an exception object, then you throw it, and then control transfers to whatever catch block manages to handle, to claim that exception type, right? Nothing new, I guess, for the rest of us. But let's try to dive a bit more. Roughly for C++, this means that we will have some user code that will allocate memory for some exception for some exception type that you are going to throw, and then we're going to throw it. Then the runtime library is going to identify somehow automatically. It's going to identify the proper catch block that needs to catch this thrown object. And then we will start some process that we call unwind that will try to undo some stack frames on your call stack, and then we will end up transferring control to the catch block, which we call catch T. So for our case study in the first slide that you saw, it might look as follows. I will try to point here. So you have this may throw function that throws here. There is a catch block in catches and rethrows. It was a catch all actually, but in between there was some other stack frame that belonged to do something that needs cleans up. And actually there is some automatic storage here that needs to be distracted. So we will see what happens here between the throws and the catch. This process is highly ABI dependent, and the runtime obviously needs some additional information that is emitted by the compiler. This is already starting to not sound very trivial. So I mentioned ABI. This is not an official question here, but who knows what an ABI is? Okay, 50%. Fine. So basically, an ABI defines the low-level details of the interface. So just to compare it with an API, in an API, you define the high-level details of how to interface with your code. That is, for example, the function name, the parameter types, the number of parameters, the return type, and whatnot. But the ABI, in turn, defines the low-level, even machine code level stuff of the interface, right? So you have data layout, the calling conventions, etc. We will see more about this in a while. For C++, we have a couple of well-known ABIs that are mostly used in all the compilers in the industry. We have the MSVC ABI, which is used by, well, MSVC. And there is the Itanium C++ ABI, which is, I would say, used by the rest of the world, mostly Clang and GCC. C++ ABI usually details what happens with exception handling, the layout of runtime type information structures, how a function call is lowered. For example, you have a member function, and obviously because it's a member function, there is some implicit parameter, which is the this, which is the instance of the object that you are invoking this function on, etc. Name mangling details and whatnot, but usually no specific calling convention. This is defined in some separate ABI. Let's talk a bit more about calling conventions. Calling convention specifies how the function arguments and return values are going to be passed. Either they are going to be passed through CPU registers, or they are going to be passed on the stack. What happens when you cross the function call boundary? What registers you can use as temporary during your function code? If you want to preserve some values of some registers throughout function calls, which ones are responsibility of the caller to be preserved, to be saved if you want to preserve their value, and which ones are responsibility of the callee to save them, and possibly some other details about the stack frame layout when you do a function call. So this is already getting a bit complex. So here, if I'm able to point, here this is how it might look for the main stack frame. When you call main, when the startup code in the C++ library or C library calls main. And here you can see that we are going to, basically the function is going to clobber the value of some registers. So we need to push them as part of the function process if we want to preserve them. And this is actually what the calling convention also specifies. Which registers do I need? And the caller expect from me. If I return back from a function call, which registers are going to stay in the same exact state? So now let's dig a bit deeper about what the Itanium ABI says about exception handling. It's basically split into 3 different stages or levels. There is the level 1, which is the base ABI, which is totally language independent. Believe it or not, it's part of the it's part of the Itanium C++ ABI, but this part is language independent. Then there it comes level 2, which is the part of the ABI that is tied to C++ itself. And then there is level 3, which is the suggested implementation, which we'll not cover in this talk for the sake of time. So let's start briefly describing what happens at level 1 and how does it work. There will be, I will start with some definitions at this stage. And the whole exception handling thing is based on what we call stack unwinding process. You might wonder, what is this? Okay, it's the control process of trying to undo or revert stack frames. It's per the level 1 of the Itanium C++ API, it's a two-phase process. We have a first phase, which is called search, second phase, which is called cleanup. We will see more about them in just a while. At each step, what will happen is that we will call something that we call personality routine. We will dive a bit more about it in just a second. And then there is this interaction between the unwinder library and the personality routine. At each step, during the unwinding of the stack, it will call the personality routine, asking, okay, is there something interesting that we need to do at this stage in the stack, or can I continue unwinding? And the personality routine will tell us, yeah, there is something to do here, or no, you can continue unwinding as usual, nothing to do, nothing interesting. So in this sense, the personality routine is basically the interface between the language exception handling semantics and the rest of the unwinding process. Now, after having defined these concepts, I would like to name the concept of landing pad. This is basically some user code that manages to catch a given exception type or perform cleanup. Cleanup as in call it destructor, because it's some automatic variable that was allocated in some scope, and it needs to be distracted when you leave that stack frame. And then we have the unwinder, which is basically the runtime component that it's able to perform all this process. There is a couple of well-known unwinders. There is the libgcc _s, which is basically what is delivered with GCC-based toolchains. And then there is libunwind, which is provided by LLVM and compiler RT, and can be used by Clang if you specify a couple of command line options. So let's try to raise an exception. How does it work at the level 1 API level? Well, the level 1 says that any implementation that complies to this API should export a function that is called _unwind raise exception, which is the one that you use to raise a language-independent exception. And this basically takes an object, a pointer to an object of this type, unwind exception, which has this structure. I slightly lied when I said that it was going to be the only C++ excerpt that you were going to see for the case study. We have this as well, not that much, but still. So basically, and most importantly, we have the exception class first member, which specifies, because recall that this is the language-independent description of an exception, right? It could work for C++, but for other runtimes of other languages as well. So the most important member that we have is to describe what runtime does this exception belong to. So the vendor of the implementation and the language, which has this value for C++ implementations. So far, so good. Let's now briefly describe what happens at phase 1 of the unwind process and phase 2 of the unwind process. So at phase 1, what we will do is to try to search. We will virtually unwind the stack. So our topmost stack frame is makeThrow, which is the function that was throwing in our case study. Basically, we will virtually unwind the stack. The changes will not be effective in that sense. And the unwinder will try to interact with the personality routine to try to search for a function that it's able to catch the type that we are throwing. In this case, catches and rethrows. But it's not going to perform any cleanup or whatever. It's just going to locate the stack frame corresponding to the function that is able to catch that specific type of exception. So the stack is not unwound. And if we manage to arrive at the end of the stack without finding any specific a specific function that is able to deal with this exception type, then obviously you know that we will terminate the execution. So the unwinder signals, okay, I reached the end of the stack, nothing to do here, terminate. So that is phase one. Phase two, on the other hand, we know where we have to land. So we have located that there is a catch block here, there is a catch landing pad here that we need to land on, and then we will actually making it effective for the unwind process. We will unstack, we will revert this stack frame here, we will revert one stack frame more, we will call cleanup functions as we progress until we land on this catch here. Finally, the execution will resume at the landing pad, at the corresponding landing pad. Don't get frightened, or yes, maybe, I don't know. We will try to dive a bit more on this as we progress. Key idea that you have to take home is that we have to make it appear as if all functions that are above us return successfully and then continue execution at the landing pad that catches. So that basically involves, think of this for a while, that basically involves calling all the cleanups that needs to be done, but also those, we briefly described what is a coalesce saved register and whatnot. We need to, in this process of unwinding the stack, we need to restore those values to the specific CPU registers. This is something that is usually done as part of the epilogue of a function, so we have to simulate this process on the go. This is already getting a bit complicated, right? Let's try to describe a bit the interface at level 2 of the API. So we have some functions that we need to comply with if we comply to the Itanium API. There is some functions which are meant to be called in throwing user code, in code from the user that actually throws an exception, and some other functions that are meant to be used in a landing pad that catches. As we will see in a short while, this function here is used to allocate a small buffer for the exception object that you are going to throw, and the CXA throw function is used to actually start the unwinding process. It's a proxy to the unwinding process. We will not talk about this for the sake of time, but feel free to ask me at the end of the session if you have any questions. In phase one, we talk about the generic language-independent form of an exception, which was this unwind exception type. But this is not actually what is being used when you throw an exception in C++ code. This is the actual underlying type, which is much more complete. As you can see here, there is RTTI pointer to RTTI type information. There is a exception destructor, the terminate handler that you had at the point in which the exception was thrown, some catch state, and hey, look, we have an instance, a member subobject of this type, unwind exception, which, if you recall, was the language-independent representation of an exception object. Actually, if we dig a bit deeper, this is more or less the layout of the whole thing. You have the thrown object here, which could be, I don't know, an integer, to the runtime error, whatever. So this is the actually thrown object. And then this is prepended a whole CXA exception type, which contains the language-independent representation. This is meant to be used by the C++ runtime, but this is meant to be used by the unwinder library. More details if you follow the link. This is how it looks to throw an exception. If you look at it in Compiler Explorer, you can use my example, you can use your own, but you will see that throwing an exception looks as this. There is some call to CXA allocate exception, in which, as I said, we allocate enough space for the object that we are going to throw. Then we construct an object in place in the buffer that this thing allocated for us. And then there is the actual CXA throw call, which starts the actual throwing and unwinding process. Okay, beautiful. Let's let's try to open the implementation for CXA throw a bit. This is how I don't want you to get lost in the whole details of the thing, but the important thing here is that, okay, by the way, this is the implementation of Live CXX ABI by the LLVM project. And this is how it looks for CXA throw implementation. Basically, the important thing here is that it ends up calling, after doing some bookkeeping stuff, it ends up calling the language independent throwing routine. There is a lot of things that are going on also at this level of the ABI, but for the sake of time, we will not deal with it because things are going to start getting complex, more complex, much more complex. There is at this level, there is some other things, but we will skip for now. The important point is that this level of the ABI specifies the how, not the where. So it doesn't state where this information is stored in your executable file. So this brings me to talk you a bit about LSB, the Linux standard base, that despite the name, it's also being used not only for ELF executables, but also for Maho binaries, which is the binary format for Mac OS and iOS. So let's dig a bit deeper. So Linux standard base says that exception frames are going to be described in this way. For the unwinder, we are going to have a representation that it's based in unwind tables. What is an unwind table? You might be wondering right now. I will tell you, don't worry. Actually, it says more. It says that it's going to be based on dwarf CFI. By the way, who here in this room knows about dwarf? Or at least heard of it? Okay. So it's well known for being a debugging information format. But it also specifies how to, describe the stack frame of a function. That's why it's used here. And the Linux standard base specification also tells you how you're going to represent the information for the personality routine. And it's going to be represented in an area that is called language-specific data area, LSDA for short. And I said LSDA, not LSD. So no drugs here, at least for the moment. Now we will briefly talk about unwind tables. What are those? This is used to frighten kids, by the way. So what is an unwind table? It looks as the following table here. This might be perfectly the description for the may_throw function that I thrown away, pun non intended, for my case study. So basically, this relates program counter value. So this is program counter value, whatever that is for your architecture. It might be the RIP for x86 platform or PC for ARM. And it specifies all the collision safe registers, so registers that are guaranteed to preserve their state after a function returns. And it specifies where they lie, where the prologue of a function push them into the stack. So this states the actual position of them in the stack. Let me try to rephrase that with an example. So this is the disassembly of may_throw for ARM64 architecture. So you can see that there is an STP instruction here. This stands for store pair. And it basically stores a pair of registers, namely, I don't know if you can read it properly from behind, but it basically says STP x29 x30 SP minus 32 exclamation mark. So this instruction basically tells you, okay, this is the pre-decrement notation. So you take the stack pointer value, you decrement 32. So that makes room in your stack frame. You reserve some stack space. And then you store these couple of registers there. So you can see here that the X29 and X30, which is aliased by the LR and FP registers. LR, it's for those of you who don't know ARM64, it's basically the link register. It holds the return address of your function, and the FP is the frame pointer, right? And basically, this instruction tells you that you have to store them at the stack. You make some room in the stack, and then you store them at the top of your stack. So that's SP plus 0 and SP plus 8. Fine. That's on our first step. On our second instruction in the prologue, we basically store a couple of more registers in the stack, this time at positions SP plus 16 and SP plus 24. Fine. And then the third instruction here, mov x29 SP, basically tells you, this sets the frame pointer value. So basically, this means that I can start addressing all these registers, not only from SP, but also from FP, which is good because SP might change. If you do a loca call to reserve more stack space in your function, then, okay, you will have to adjust here the table, which is not good. So addressing anything that is on your stack frame is pretty much preferred using FP, right? If you look at this table, you might imagine that, okay, for a real world program, this might look like really, really large, like several hundred megs or even gigabytes, right? Just imagine how it would look like if you describe what each stack frame of each function looks like at each different point in the program. So it can just imagine that for a real world program. It gets really, really big. So we need some form of compressing this table. And it should be fairly trivial, between quotes, to compress it, because you can see that most of the table stays the same, except for some deltas. So you apply some deltas here compared to what we had. Then there is the delta here, which is that we can start accessing. Go ahead. Probably J. Daniel can give you the microphone.
Could you please clarify? So you said, imagine how the table looks if any function is called on with any particular like call stack, like all the combinations of how the function can be called.
The actual combination doesn't matter because your function prologue is going to reserve some stack space to do something, something, something. It's going to push the value of some registers into the stack that needs to be preserved because you are going to clobber them, right?
So basically,
then it doesn't matter where you enter that function from. It's going to do exactly the same every time.
Okay, exactly. The size of the table should be proportional to the number of throwing functions, more or less. Yes, no?
No, because so basically this table specifies everything that is known for a particular point in the execution of the program. So given the program counter, it tells you, okay, this register was saved at this position in the stack, this register lives at this position. Even if it's a C function, just think of the following. You have C++ function that calls C function that calls C++ function. Even if the C function needs to be unwound.
And this table is dynamically updated as the program goes?
No, this table is constructed by the compiler. Good question, by the way. So at this point,
I'm confused.
Well, I will. Okay, nice question. I will elaborate a bit more in a couple of slides.
Do you want me to take more questions? Or?
Maybe at the end, for the sake of time, probably.
If it is not essential for following the discussion, I prefer at the end. If it is a clarification, it is okay to ask.
Yeah. Okay.
What I do not understand is how it can be constructed. How do you know what the program counter is going to be? Because any function can be called from any place. So how does it know what is going to be the program counter?
Yes, and actually you could have, this program could be loaded in any position of the virtual address space, SLAR, whatever, fine. Because this table, that's why I said conceptually here, even though I skipped over it while speaking. Basically, each function has its own table. We will see how it is encoded.
It is an offset from the beginning of the function, or?
Sort of, yes.
Yeah.
Actually, I wanted to talk about it in the next slide, actually. You can see these .cfi directives for the assembler. I don't know if any of you saw them before, but this is telling us exactly this information. We will see how it is encoded. Okay? But thank you for the question. We will see how this works. But yeah, the conceptual form is exactly this. You have some big table, like could be several gigabytes, that tell you for each of the program counter values, okay, I have this and this and that in this position of the stack. Conceptually, it's this way. But in reality, it works a bit differently. We will see now. So basically, this is very, very, very space and time consuming. So we need a compressed form, and that replies to your question. So we need a compressed form, and that's where dwarf standard comes in, actually the section about call frame information. But first, I need to describe a new concept, which is called CFA. CFA stands for canonical frame address. And basically, this is sort of the value that the stack pointer had when we entered the function. So we have an example here. This is ARM64 again. So we have BL, which is branch and link, function call, that is. So we do function call to make throw, fine. So the value of the stack pointer at this exact point in time is what we call the CFA for this stack frame. So this is the previous stack frame. This is the stack frame that is going to be constructed for make throw. But before the stack frame is constructed, the value that the SP had is called the CFA. So all the registers that are going to be pushed in the stack as part of the prologue can be addressed in relative terms with respect to the CFA. So the X19 register can be addressed via CFA -8. The X20 register is CFA -16, and so on. Mind that this is decreasing addresses because it's the stack, right? That's why the minus. So now let's return back to the previous screenshot from Compiler Explorer. And now we can start making sense out of these directives here. Okay, CFI offset for W19, which is sort of an alias for X19. Oh, look, -8, -16. Look at this image here on the right. So W19 or X19 is located at CFA -8. W20 is located at CFA -16, and so on. So basically, what we have is the following. That complex table that you asked for can be encoded in the following way. This is going to get really complex. We can encode it as a CFA rule that describes where the CFA, where the canonical frame address lies for a specific function. Basically, a rule that describes where to point for CFA, plus where are each of these independent registers being stored. So you can see here that we have CFA start proc. This basically is a directive. I'm not going to dive in too much on that one. But basically, it creates some initial. So the assembler will create an initial CFA rule for this. And then basically, the initial rule is CFA equals SP, as I said. Okay? And then we allocate some stack space, -32. So 32 bytes of stack, fine. And then look, we correct the CFA address by 32. So we sum 32 and we point again to the whatever was the previous CFA value, which is so basically whenever the stack pointer moves, we have to compensate for that to still point at the same address, right? And then the rest of the registers can be encoded in terms of a specific offset with respect to the CFA. So far, so good. So at this point, and this is mind-blowing, you can start thinking of your C++ program as 3 different programs. There is the program that runs at runtime, at compile time, and then there is 2 programs that run at runtime. Your regular stream of machine instructions, and some opcodes that describe what is to be done when we unwind. So we have some sort of virtual machine, which is the dwarf virtual machine, that it's able to interpret these opcodes to correct the CFA address and to address specific registers and whatnot. Okay, so far so good. Importantly enough, we have this advanced log here. So basically, with these opcodes here, we are describing the deltas, and this last opcode describes where to apply the deltas on this conceptual table that we had, more or less. So yeah, complexity is getting a bit high at this point. Obviously, we prefer FP-based rules because the stack pointer might get changed at any time during the function code, right? We might reserve some more stack space at any point in time. So describing the CFA via FP is always preferred. Now we will dig a bit deeper on where this information is stored in the binary, because I said, okay, the compiler actually emits this information. It emits machine code, but it also emits these CFI opcodes for the unwinder to be able to unwind the stack frames. Where is this information? So if we call LLVM object dump on our compiled case study, we will see that there is some sections in the binary. We have EH frame. EH stands for exception handling, by the way. There is EH frame header, EH frame, and GCC accept table. So far, so good. We will dig a bit deeper on each of those. Let's start with EH frame. So what is this? It basically, it's a collection of what we call CFI records. CFI stands again for call frame information. And they can be of two different types. They can be CIE, which is common information entry, or they can be of type FDE, which is frame definition entity. Altogether, they form a two-level hierarchy, such as, if I can point here, whatever. They describe a two-level hierarchy where we have the CIE at the top. There can be any number of CIEs and some number of FDEs that depend on that CIE. This number that you see here is the identifier for that CIE or FDE. It basically, it's either the absolute offset with respect to the beginning of the executable image or some relative offset with respect to this section, EH frame. Let's dig a bit more. This is starting to get like an infinite rabbit hole, right? So a CIE contains some code and data alignment factors, basically, because when you address things on the stack or basically on your program, instructions, whatever, usually there might be, all the addresses might be multiple of a certain amount. So for example, slots in the stack are expected to be multiple of the word size of the platform, so to say. So if you are pushing register, probably is the size of a register and whatnot. So basically, storing this common factor will make us specify all these numbers, all these offsets with respect to CFA and whatnot, as exact multiples of this factor, which results in smaller numbers that needs less bits to be encoded. It contains also the return address, register, some augmentation string. This is very important because it describes additional payload that could come with the CIE or FDE. Specifically, there is this. So it's basically a character string that, depending on the specific characters that you find out there, it signals the presence of some additional bits of data, right? So if the augmentation string starts with set, it means that, okay, we have some additional payload. We need to be cautious because there are some additional things that we need to pay attention to. If we find a capital L afterwards, it means that we have some LSDA information. Recall, LSDA, it's the language-specific stuff for dealing with exceptions, right? Because at this point, we are only talking about the unwinder and unwind information. So this relates to the other part, which bridges to the knowledge, the language-specific knowledge about exception handling. and the P, which means that we have a personality routine attached to this to whatever FDEs that might use this CIE, and of course some initial CFI opcodes. On the FDE side, we have some program counter range. I don't know how I'm going to with respect to time. On the FDE side, we have a program counter range that describes which range of program counter values this thing applies to, some augmentation data, and the CFI program. I hope that this becomes a little bit more descriptive with this image. So we have a CIE, which has some augmentation string, which I will explain shortly, some align factors, the return register, initial CFI instructions that are going to be prepended to whatever is described by the FDE. And yeah, let's briefly describe this thing. So set means that we are going to have some payload, which is here and here, by the way. P means that we are going to have some personality routine, which I have highlighted here in magenta. When you see this bullet here, it means encoding, because there is several encodings that, I mean, when you point to something else in Dwarf, you could either point in absolute terms or you could point in relative terms, and you can use that, that size, like 32-bit pointer, 64-bit pointer, or whatever. So this is basically specifying which encoding are we going to use, and this is the actual value of the pointer to the personality routine. Then we go to the L, which means, okay, there is LSDA information, and here we only have the encoding of the LSDA information. The actual data, the actual pointer to LSDA, is part of the FDE. Why is that? Because both the encoding and personality values are going to be reused by several FDEs, but we expect that distinct FDEs are going to have the distinct values of LSDA pointers. I hope that gets clear enough. And then the actual opcodes that are part of the FDE. For the sake of time, and this is getting a bit longer by now, I won't dive into the actual serialization details of how this transforms into a sequence of bits in your executable file. But if you want to see more details, you can look at this reference here. Then we will quickly talk about the EH frame header. There is not much to talk about this, actually. It's basically, you can think of this section as an index over the previous section, over the EH frame. So basically, this is storing that many values, FDE count, of this structure here. And this structure here has some initial location, which is the program counter value, and some address, which is the FDE that it relates to. These are ordered with respect to the initial location, so we can do binary searching on this. So you can just think of this as an index, where we can do binary searching. Last but not least, on this side, we have this section, which I didn't describe before, and it only applies for Mac OS and iOS platforms. And it basically tries to summarize both sections that I described, EH frame and EH frame header, in a single section. And it's very, very efficient representation that manages to, given some assumptions that I'm not going to talk about right now, it manages to represent the whole unwind information for a given frame in just 32 bits. So very, very, very efficient. But bad part, it's that it only works for Apple platforms. Now we will try to dig a bit on how LSDA information is being recorded on the binary format, right? We will talk about LSDA for the GXX personality v0, which is the default personality routine for both GCC and Clang. So most likely, if you are compiling your applications with GCC and Clang, this is what it is using. So basically, this section looks as follows. We have a collection of exception tables, which is basically collecting different, the information for this section is being collected by the linker, collecting together different tables that comes from different translation units. But if we look at a single table, it looks as follows. We have a header, fine. We have some call site table, some action table, type info table. The call site table basically has a given number of entries that describe a program counter range, what is the landing path that we need to jump to if something happens, And these actions describe what needs to happen for us to jump into the landing pad. More on that in the next slide. This section, on the other hand, type info table, describe basically it holds pointers to RTTI type information and the exception specs. We won't talk about exception specs today because it's meant to represent something that it's related to dynamic exception specification, which was there up to C++ 17, so not there anymore, so not important for today. But type infos, as I said, it's pointers to RTTI type information. Usually there is an additional indirection level. So we are not storing directly the pointer to the RTTI type information, but some pointer to some area that actually points to where the RTTI information for that type lives. This is this way to support relocations by the dynamic linker. If you want more information on that, just ask me after the talk. Again, we are not going to dive into the actual details of how this information is being serialized into a stream of bits in your executable file, but you can click that link at home and you will see there is a really large comment that describes the encoding. If we dig a bit deeper into the call site table, which remember was a part of the exception table, we will see a given number of entries, each of which has some program counter range that it applies to, the landing pad that we need to jump to, if we need to handle one of these chain of actions. If we need to catch T or catch T2 or whatever, the types that are catchable at this landing pad, or there is another type of action which is called cleanup, which is, okay, we need to jump at that landing pad if there is cleanup to be done, if there is some destructors to be called. Hopefully, you will understand much better when we go to practice in just a while. Now, to awaken you up a bit at this point, I would like to launch my last question about the C++ trivia. So, can we catch exceptions so far, up to the knowledge that we have? Can we catch exceptions if we build our translation unit with fno-rtti? What do you think? Who think we can? Without? Sure? Okay. Who thinks we cannot? Okay. And the rest neutral, I guess. So the answer is that maybe it depends on the implementation, actually. So most likely your compiler, if you use Clang or GCC, it's because if I go a couple of slides before here to this slide, LSDA is actually pointing to RTTI type information. So to be able to catch an exception of that type, we need to have RTTI information for that type. Otherwise, it's impossible. So what the compiler does, if you compile your translation unit with fno-rtti and you have a catch for a specific type, it will generate RTTI type information in a minimal form, at least to catch exceptions, for that specific type, and only for that type. And as Louis Dion pointed out, this might be fragile, so don't rely on it too much, but it might work. Now, okay, theory is good, but let's accompany it with some practice. Let's see what works and how it works, and let's try to make sense out of the whole explanation that I did. But first, let's do some recap. So we have CXA throw, which is where the actual throw happens. That manages to call the language independent form, which is unwind raise exception. That starts this process of, which is two-phase, of stack unwinding, right? Where at each stack unwinding step, the unwinder is going to call the personality routine, okay, is at this point in the stack, do we have anything interesting to do or not? And it's going to react on that information until we do that, until we arrive to a catch landing pad that it's interested in catching that type of exception, while performing all the needed cleanup, so calling the structures along the way. And where all this information is stored in these specific sections in the executable file. Recall our case study that I gave in the first part of the presentation. So you don't have to memorize the code. in its entirety, because I'm going to show it at all times, mostly, on the right-hand side. Couple of comments. So what I did here was to run this example. Basically, it was compiled on a new Linux platform for ARM64 on this version of Clang. And I am using leave and wind, LLVM leave and wind, compiled with debug in debug mode. What does it mean? It means that it adds some instrumentation to the library, so we can actually follow the unwinding process. We are going to see how this works, and it's going to get interesting. To enable it, if you have such a leave and wind version, you need to export these environment variables, and we didn't talk about it. You can ask me later if you want to know more. We didn't talk about it, but there is synchronous unwind tables and asynchronous ones. We are going to use the asynchronous because they get shorter. I hope it's readable. So let's follow the execution. Let's get to the throw point first. So we start in main, right? We construct our vector, presumably on the stack. Then we call catches and rethrows. Fine. Here, what you can see here in the lower left corner is a LLDB debugger session. And what you can see here is the standard error output. Recall that we linked against the debug version of leave and wind. So we are going to see lots of debugging stuff here. First thing that you need to notice, this is a dump of some of the Collie safe registers, not all of them, for ARM64. Hope it's readable enough, but it says FFF FA58. I want you to remember that number, because if all the explanation that I gave you is right, when, okay, we are going to do some function calls, whatever, but by the time we reach this catch block, we should be at the same exact state. We should have the same exact state in our Collie safe registers. So FA58, okay? We call catches and rethrows. Control is here right now. Some string is constructed in automatic storage, presumably stack. Okay, fine. We call do something that needs cleans up. Here's the dump again of the Collie safe registers. Here is do something that needs cleans up. Yada yada yada. We call main throw. I forgot to highlight it here, but this is again the register state, Collie safe register, some of them. And here it says C1230. Okay, remember that number as well. We go to main throw, fine. The execution is meeting this condition, so we are going to throw. I stated before that throwing is basically a call to this function, cxa throw, which is given by your runtime library. And we are going to enter the process of unwinding. Welcome. So I maximized the standard, the window that contains the standard error output, and we are going to follow what the unwinder says. So basically, the unwinder is looking at the top of the stack. It says anonymous because I didn't compile with the debugging symbols. Fine, but you have to trust me. This anonymous is maythrow, is the top of your stack. So it tells me that, okay, you have to continue unwinding. There is nothing interesting here. We entered the phase one, by the way. We entered the phase one, so we are looking for a landing pad that is able to catch the type that we have thrown, which is runtime error. So we notice that there is nothing to do here. I don't know if you can read it, but at the next, so we virtually unwinded one stack frame to arrive at do something that needs cleans up. There is nothing to do here as well. But look, phase one exited with handler found in the third stack frame, which belongs to catches and rethrows, basically. So phase one stopped, and we are going to start phase two now. So phase two starts. I restore the window again so that you can see most of the stuff. So the unwinder, the system unwinder library, started ripping off one of the stack frames and restoring all the Collie safe registers that were part of that stack frame. And you can see that we reach a landing pad here. There's no catch, but it's a cleanup because we need to destruct this vector here. most importantly, you can see that, okay, this C1230. So we re-entered the landing pad at this, in this function and do something that needs cleans up with the exact same state that we had before calling main-throw. Then phase 2 continues. We arrive at this landing pad here, and we arrive with the exact same state. Again, we have this FA58. So the unwinder restored all the callee safe registers that were pushed into the stack. It located them. By the way, you can see all of the dwarf opcodes that were processed here: DW def CFA, DW CFA offset, yada yada yada. Basically, it restored all the state, and we re-entered the catches and rethrows function with the exact same state that we had in terms of, the guarantees of the ABA, which basically it's a cohesive registers and whatnot. And we arrived at this landing pad with this state here. Then we are going to do some rethrowing, which is basically it's a call to CXA rethrow. And then the same process happens again. I'm going to maximize the window. We look at this stack frame for catches and rethrows, which doesn't have any handler, but it finds a handler just below in main. So phase 2 of the process starts again. This basically yields us to landing in a landing pad that is here at the end of the function, which basically destroys this string that had automatic storage. And then phase 2 continues. We reach this landing pad here, which catches the type. And we see that the callee saved registers had the exact same state before we called catches and rethrows. This was beautiful. Wrapping up. We didn't talk at all about Windows exception handling, but basically for 64-bit platforms, it works pretty similarly to what we saw here today. And for 32-bit platforms, it has some differences. I'm going to skip the details for the sake of time. Key ideas for you to take home. Exception handling is a very, very complex process, but it's really amazing. That involves so many specifications and ABIs. And there is this beautiful dance that we saw between the unwind routine and the personality routine, going back and forth. All this information that is needed for that, it's stored in specific sections of your executable file format. And I didn't show any specific numbers, but it's not a generally fast process because of all the things that need to be handled. Some references, if you want to check at home for the specifications and whatnot. It's very tedious to go through them, but still. And thank you. Thank you for listening.
Thank you very much.
And now questions.
Yeah, sure.
Thank you very much. That was intense.
As light as it can be.
Yeah. I got the idea that the process is pretty complicated. Let me ask a really simple question. So when there are no exceptions thrown, even though we're prepared to handle them properly, but on the workflow without exceptions, I live in the world where I assume that overhead of existing exceptions, the exception handling is basically zero. But what are the penalties actually that what is the overhead on the happy path when we do not throw any exceptions? Is there any? And yeah, can you comment on that?
The answer to your question is this is so complicated. So complicated just because of not sacrificing runtime performance for the no exceptions path. So the overhead for your normal control flow is absolutely zero. Zero.
But that is in execution time, not in binary size.
Yes, in execution time. In binary size, you have this, it's a few slides ago, but you have these sections that describe unwind information and whatnot. Execution time is exactly the same. If you don't throw, yes, exactly the same. But you have some overhead because this information has to live somewhere, right?
And the landing pad somewhere in the code section, I assume.
It's usually some sections in the data segment usually.
Well, first of all, thanks. It was very interesting. My question is, as I understand that this table is compressed, it's still generated even if you turn off exceptions when you're compiling, right?
Yes. You have a couple of switches that are, it's pretty long, so yeah. F-no asynchronous unwind tables, and then you have F-no synchronous unwind tables. If you disable both, then there will be no unwind information at all. And if you disable so if you do F-no exceptions as well, there will be no LSDA. So if you combine the three flags, no LSDA and no unwind at all.
All right, thank you.
I know very little to say. Well, basically, I know nothing about this stuff. This is very, very interesting. But you said at the beginning of the talk that throwing is non-deterministic in time. And what I saw seems to be like complicated, but deterministic. So where's the catch?
You don't have, so the time, the upper bound of the process is given by the size of, basically by the number of stack frames that you have. You know that in advance? If you know that in advance, you can time bound the thing. If you don't know.
So the problem in general is that you cannot perform a worst case execution time analysis, which is required in some hard real-time systems.
Do you have an estimate of how much executable size do I save if I replace all throws by terminates and print this is an error?
Can you repeat the question? Estimate
how much executable size would I save if I replace all my throws by terminates or panics, if you prefer?
It depends on the size of your program, basically. It depends. Actually, as I said, the whole unwind information thing, it's very, very compressed using these opcodes and whatnot, but it really depends on the amount of functions that you have. And it depends on the complexity of the function as well. Even though the compiler usually uses FP-based CFA rule, if it cannot, for whatever reason, because you compile with a no frame pointer, whatever, basically it will revert to representing everything with a stack pointer-based CFA rule. And if you do reserve a lot of stack space and then you do a loca or reserve something and then return it back. So it actually depends on your code. I cannot.
So that was the implementation answer. My more general answer is, if you can do that, then you don't need exceptions. I mean, exceptions is when you locate that you have a problem in one place in your code and you need to handle in a different context. That's it. And of course, it's not either a control flow mechanism. Before the next one, I have a question for you while I throw out the mic. Now you are in the committee. So if you had a magic wand and you could change things, what can we do to simplify the process? For example, imagine that we decide something like, we do not allow absolutely anything to be thrown, because today we can throw an int or we can throw a double, and we make some restrictions or other kind of restrictions. Can we simplify the thing? And the second is, can we make simplifications in the ABI? Because, I mean, we deprecated things in C++ 17. We should be getting rid of that. And now,
that is that calls for a non-short answer, I guess, because you have to think that you have to also support. Okay, your C++ code might be called in C code, that might be called in C++ code again. So you should be able. I mean, you have to ensure that the ability to unwind the C stack frames remains there. And those C functions, or actually it might be even manually written assembler functions. So you still have to support that. So it's not very trivial to arrive to a simplification.
Hi, thanks for the talk. You briefly touched upon structured exception handling on Windows, right? On one of the slides.
On Windows.
On Windows, yeah. And do I understand correctly if you have like a C++ code on Windows that uses both standard ISO C++ exceptions and the extension __ try and catch, they both go through the same machinery that you described, or is it completely different?
What I have described is basically how it would apply for any system that operates with Titanium C++ ABI. But if you are on the Windows platform, most likely you are compiling with MSVC. And if it uses the structured exception handling, I guess I'm not an expert on unwind exception on exception handling for Windows platform, but I guess it should use the same mechanism as the __ try. That's why I mentioned it here. So it should rely on the inherent features of structured exception handling for the platform.
Great talk. I have a question. Are you familiar with the work by Kalle Lestel that he was providing keynotes last year on a few conferences, maybe the year before as well? He claims that he can simplify or improve the performance of the exceptions multiple times. And how it's your point on this one? Is it possible or not in general way? Because he was doing this for his specific platform he handles, not the generic implementation.
I'm not sure. We can discuss that offline because I mean, this thing is so complex because it has to be very, very generic. So it has to handle even code that I could write like manually in assembler, right? So given some assumptions, it might be simplified. And that's why I briefly mentioned the Apple compact unwind standard, well, standard ad hoc standard. So basically, it could be simplified, yes, but at the cost of making some assumptions. So whether or not that assumptions, I mean, it's a complex topic, so we can discuss.
Short answer.
Yeah.
Okay, thank you for a detailed talk. With a more practical question, you mentioned there are different libraries that implement stack unwinding and on. Are there a significant difference in performance between them? And is there any winner? And the second short question, exceptions should be allocated somewhere. So is the stack unwinding affects multi-threading code because you need to synchronize? Thank you.
Very good questions. For the first one, there is. I didn't came with specific numbers, but there is performance difference. And actually, there is a couple of different leave and wind implementations. So there is three. I didn't mention. There is the GCC one, the LLVM one, and there is the original one, but by HP. And basically, most smart implementations do some form of caching. So whenever you know the FDE that describes what you need to handle and whatnot, it gets cached. So the next time you throw the same type of exception, it knows what to do. Some other implementations do not cache anything. So they are worse in that regard. Okay. For the second question, what was it? The second question, can you remember? The allocations, yes. Usually the level 3 of the ABI, which I didn't mention today, level 3 describes exactly that. You cannot allocate on the stack because the stack is going to be unwound, right? So this usually lives on the heap. And there is even guarantees where there is even some guarantees, emergency buffers and whatnot, on what happens when you don't have enough memory.
Okay, I think this is going to be enough. So thank you very much for your detailed presentation.